Okay, I think you're good to go.
Oh, thank you. Hi, everyone. Thanks for being here and thanks for having me. My name is Dustin Morrill. I'm a PhD candidate here at Amii under the supervision of Michael Bowling. And this is the work I've done over the last year with a bunch of great collaborators over many different institutions. And this is work on playing multi-agent general sum games robustly without knowing what strategies the other players will use ahead of time. So I'll just jump right in. There we go. So this is, we have two papers on this now. One is called Hindsight and Sequential Rationality of Correlated Play. It was at AAAI and it's also on arXiv. The second is called Efficient Deviation Types and Learning in Extensive Form Games. It's also on arXiv and it's just being reviewed right now. This talk is mostly going to focus on the first one that sets up a lot of basic ideas that we build on in the follow-up work. So I'll cover how ideas about how we should design algorithms to play multiplayer general sum games. A lot of it, the technical details won't be new, but we're trying to package it up in a way that will help researchers use it more readily and give a coherent framework for thinking about solid, well-grounded algorithms for playing these games. Then I'll talk a little bit, I'll give a tease of the empirical performance improvements we can get by taking this view. And then I'll go into some technical background so that I can describe the next bit. So it's going to be, the technical stuff will be on extensive form games, and I'll talk about different ways of designing algorithms in extensive form games, and I'll get into more about all of this. Then I'll show some new results for an old algorithm called counterfactual regret minimization that's been really popular and successful in solving zero-sum two-player imperfect information games like poker. And so we have some new results to understand it in more general games. What I won't get to in this talk is observable sequential rationality. This comes at the end of our AAAI paper. I think it's a really interesting extension to the traditional notion of sequential rationality in game theory, but I just won't have time for it today. And as well, a new algorithm that we have in our second paper is called extensive form regret minimization that builds on all of these ideas. I will mention it briefly, but I won't go into the details about this. Okay, so I'll get into the first bit, thinking about how broadly we should design algorithms to play multiplayer general sum games. And so I'll start with a kind of common approach that we're calling the artifact approach to game playing. This is where we take a game, we do some computation on it, and we have that computation spit out some static artifact, some fixed strategy that we're going to use to play the game in the future. And ideally, this strategy is rational or optimal in some sense. One way that we often do this is we'll take a learning algorithm, we'll put it in every position in the game, and we'll have those learners all play together, training over time, and eventually we'll extract some testable artifact, again, a fixed static strategy that we'll use to play the game. This works really well in single player settings because, of course, we can just find optimal strategies. So in principle, at least this problem is kind of solved. It's also really effective in two-player zero-sum games because we can find strategies that maximize the minimum payoff for a given player, irrespective of what that other player does. So these are called maxi-min strategies or Nash equilibrium strategies. And this is what we've used to play poker in the past. And they perform really well because of this guarantee. This is not so effective in multiplayer general sum games, though, because even if we extract a Nash equilibrium strategy, and that can be difficult, that strategy can perform arbitrarily poorly, depending on what the other players do, even if those other players are themselves playing a Nash equilibrium, because there's an equilibrium selection problem going on here where different equilibria aren't compatible. So this poses a problem for the artifact approach. And what we're suggesting is to get rid of this training and testing split altogether. Instead, we're going to focus on the learning dynamics alone and come up with a rationality objective for a learner. And in practice, right, the idea is that you'll just deploy a rational learner out in the real world where this game is. So here we have the setup or what the learner sees in these dynamics. So we have a learner playing some strategy pi I, sends that to the game. There are other players here that choose a strategy as well. And then all the players are assigned a payoff according to the way the game plays out. And then the learner has the opportunity to learn from those payoffs to improve their strategy. And the process continues. So this game is played repeatedly in rounds. This is really just online learning, if you're familiar with that. And the important bit here is that we can focus on just the learner because we've bundled the other players together with the game. So now it looks basically like a non-stationary environment from the perspective of the learner. So if we unroll this process after T rounds have been played, we can see that the other players and the learner have all produced T strategies. And by uniformly weighting across these rounds, we can get a final score for the learner, just the average payoff that the learner received over time. Now, one problem we have now is that this score actually doesn't tell us in any absolute sense what how well the learner did. We need some way to compare it to other things the learner could have done. So most generally, we could just have another set of strategies that construct a baseline score from the utility functions that the learner observed across time. So now at least we can compare these two averages and see how well the learner has done compared to these baseline strategies. Another problem, though, that we've run into is that if we don't restrict the way these baseline strategies can be produced, this baseline could be extremely unrealistic. So these baseline strategies could in fact be best responses to the strategies that the other players will play on the next round. So it would have to know the future. And this is really unreasonable. So instead, we're going to restrict the baseline strategies to be constructed from a deviation function, denoted here by phi. So this is going to be a function that's fixed across time, but it's a function of the behavior of the learner. So it gets to look at the learner strategy and choose a new strategy based on that. And this will give us a reasonable baseline. Again, we can just compute the average score. So finally, we have that an objective that looks back across T rounds and asks if the learner's score is at least as good as the score from the best deviation across some set. We can start with some set of deviations and look at all the scores that we could have gotten had we changed our behavior in this way. So if the learner can achieve this constraint, then the learner's behavior is rational in hindsight. We've set up this hindsight value objective. So if the learner is optimal with respect to that objective, the learner's behavior is rational in hindsight with respect to this deviation set, and that'll become important. All right, so because we're now we've constructed this rationality objective by unrolling this process and looking back, we call this hindsight rationality. We can compare this hindsight rationality paradigm with the statements that we can get from the artifact paradigm. So in two-player zero-sum games, the artifact paradigm gives us this nice result that says that if some player I plays an equilibrium strategy, then player I's value will be at least as large as they could have gotten had they applied some deviation function phi against any possible opponent strategy. But as we saw, there's no such guarantee for arbitrary other player strategies in multiplayer general sum games, and that's why we were trying to move away from the artifact paradigm. And so the hindsight rationality paradigm gives us this, in that we have now a statement about the rationality of a learner, a dynamic adapting learner for any game. So if player I plays the sequence of strategies generated by a learner, then that player's average value will be at least as large as the average value that any deviation could have achieved, with some sub-constant wiggle room that's going to 0 over time for all deviations. And we call this property hindsight rationality. And this rationality, in fact, gives us slightly different but also meaningful equilibrium properties that we can talk about. So if all players are hindsight rational, then the sequence of strategy profiles that were generated over time forms an approximate mediated equilibrium for phi. Now, you may not have heard this term mediated equilibrium, but it's basically just an extension of equilibrium from static strategy profiles to distributions over strategy profiles. And the most famous version of mediated equilibrium is correlated equilibrium. And I'll mention later how what deviation set you would have to use to get correlated equilibrium. And if we go back to two-player zero-sum, we actually still get a nice connection with the artifact paradigm. This is, in fact, what makes hindsight rational algorithms useful in, or historically has made them useful in two-player zero-sum games, is that if all players are hindsight rational, then if you marginalize out the strategies generated by each player just by averaging them, then we get an approximate Nash equilibrium for the deviation set. But now some of you may have noticed that these technical results actually aren't new at all. They're actually the basis of online learning. We could replace everywhere where we talk about hindsight rationality, we could say no regret. So if I plays the sequence of strategies generated by a good learner, then their regret has to be sublinear for all deviations in your set phi, and this is called the no regret property. And if we have the no regret property, of course, we get the other statements as I mentioned before. Now, so the idea then of hindsight rationality, this whole paradigm, is to package that together so that people can use it to design as a designing philosophy for algorithms that target multiplayer general sum games. Now we can see what the whole procedure picture looks like under hindsight rationality. So here at the top of the diagram, we have some algorithm that we're going to deploy, and it's going to become a learner in this online learning process. That learner is going to play strategies in the game and learn over time simultaneously. And remember that this bit is actually where the actual problem is. Like the problem we're trying to solve is represented by this game, and we're going to deploy a learning algorithm to solve it. After we've gone ahead and deployed the learner and it's played a bunch of rounds, or as it's going, we can record, if we wanted to, after, like post hoc, we could record the strategy profiles generated by all the players, and we could evaluate the performance of the learner in terms of the regret, or we could check if the strategy profiles form an approximate mediated equilibrium. But again, we're not going to contrast with the artifact paradigm, we're not going to use that mediated equilibrium to solve our problem. The learner's behavior was driving the solution to our problem. And then this gives us, admits a natural kind of design idea, which is to design learning algorithms that efficiently minimize regret for some class of deviations that you're interested in. And so we've effectively reduced the problem of designing algorithms to designing deviation sets and simultaneously designing algorithms that are efficient to use those deviation sets. So that's where we're going to focus a lot of the rest of the talk on, in particular, the structure of these deviation sets in games with sequential decision making, like chess or checkers or poker. Does that all make sense? I want to take a brief break and see if there are any questions. All right, I guess if there are no questions, I will move on. So now I want to give you a hint of what we can gain by taking this view. So here I'm going to show you some learning curves in 2 different games. The exact details of the games aren't really important here. I'll tell you the details that are important. So the first game is Goofspiel. This is a 2-player imperfect information card game. And importantly, this game is zero-sum because at the end of the game, you either win or you lose. And then the other game that we'll have is Sheriff. So this is a small version of the Sheriff of Nottingham board game, if you're familiar with that. Again, it's for 2 players. And importantly, this game is not zero-sum. I'm also going to show 2 different learning regimes. The first one is a little bit simpler. It's where we're going to have the learning algorithm play against an oblivious but non-stationary player. So the other player isn't going to be able to react to the decisions that the learning algorithm makes, but their strategy will be changing over time. All right, so here are the results. We have the rounds on the x-axis, and we have the average payoff accumulated up to that round on the y-axis. In Goofspiel, the average win rate is the average payoff. And we have 3 algorithms. These are actually all instances of a more general meta algorithm. The only difference is that they're using different deviation sets. They're minimizing regret with respect to different deviation sets. So CFR here is counterfactual regret minimization, and it's a really, like I said before, a popular and successful algorithm for solving 2-player zero-sum games. And then the second algorithm we have here in magenta is PGPI, or policy gradient policy iteration. It's essentially the hedging there in the legend is just that it's a parameter-free version. And so, policy gradient policy iteration as well is essentially a dynamic programming version of policy iteration, which you might be more familiar with. Of policy gradient, mind you. So, right, and recall that the only difference is the deviation set. So you can see that there's a big difference going from PGPI to CFR in these games. Now the third line, the blue line EFR, is extensive form regret minimization. That's actually the name for the umbrella algorithm. But here, this EFR line represents EFR instantiated with a deviation set that's stronger than both PGPIs and CFRs, like strictly stronger. It includes all of the deviation, both of those deviation sets. It includes the union. And we can see here that when we do that, when we include the union, we get even better performance than CFR. So these results alone actually tell you something interesting, that even though CFR looks like it's doing a lot better than PGPI, there's actually still some interesting strategical value to the deviations that PGPI is using. And so once we use that in EFR, we get a benefit over both of them. Now in the second scenario is round robin, where we just have all of the algorithms learning together in a round robin fashion. So both players in both of these games are playing and learning at the same time. So a little bit more realistic, but also more complicated to reason about. But here we get similar results. The ordering is largely the same, with EFR on top, CFR in the middle, and PGPI at the bottom. In Sheriff, the difference between CFR and EFR is a little bit less. It's mostly, the difference is mostly in how stable CFR's average payoff is, but there's still a big gap between PGPI and CFR or EFR. All right, before I move on, any quick questions about these results? Okay, so this is all I wanted to talk about in terms of experiments for now, just to, so hopefully now you're a little bit convinced at least that this is a fruitful way forward. And so now I'm going to talk about how we should maybe think, how we can think about deviation sets in games like Goofspiel and Sheriff, where you have to make decisions sequentially. So to do that, I'm going to have to talk about extensive form games a little bit. So now extensive form games can be drawn out as a tree. Every outcome of the game is just a leaf node in this tree. All of the internal nodes are called histories, and these are where the places where players have to make decisions. And the edges are actions that connect the histories. All of our trees are finite, so all of the paths terminate eventually. And so here I'm showing 3 terminal histories, Z1, Z2, and Z3. And that's where payoffs would be given to the players. But this structure is constrained to be turn-based, right? So we have one player taking an action and another player taking an action. If we want to represent even simple games like rock, paper, scissors that have simultaneous moves, or more complicated games like poker with hidden information like people's cards, then we need to introduce what are called information sets. These are just bundles of histories where the player who acts in those histories can't distinguish between them. So I've drawn them here, and what this magenta ring is telling you is that player 2 here doesn't get to know whether player 1 shows left or right at the beginning of the game before player 2 has to act. So essentially, in practice, this means that player 1 and player 2 are acting simultaneously at the start of the game. And so, oh, sorry. Okay, so this is a really detailed, precise version, way of visualizing extensive form games, but it's actually not going to be the most useful way for us to think about how algorithms or players would play these games. Instead, what we need to do is take this tree and convert it into information set trees for players. So these trees represent the subjective view of the world that each player has as they're making actions. And this is what our algorithms and deviations will act on. So you can see here that I've drawn out on the left player 1's information set tree, where they take 2 actions in sequence and separated by outcomes that are external to them caused by the second player. And on the right, we have the second player's information set tree as well. If you're familiar with Markov decision processes, you'll see that they look familiar, and that's for good reason. They are in fact Markov decision processes, except they're restricted in that they're not allowed to have loops. And so this gives us allows us to say a lot of things about these games that you couldn't necessarily say in a more general framework. Though moving to more general frameworks is actually an interesting point for future work. Okay, so I want you to hold these information set tree view in mind when we talk about the rest of the talk. We'll reuse these figures a lot, actually. So here I'm going to show, I'm showing a different game, just an arbitrary example game. And here I'm just showing player I's information set tree. We have 3 outcomes here. And so now I want to show you what a strategy looks like in this game. So for example, here's the always left strategy. We just have arrows pointing all left, and eventually the player ends up in the LLL terminal history and gets the utility there. Now I want to show you what a deviation looks like in this kind of game. And remember that deviations are functions that map strategies to other strategies, which I'll show more. But here's one example deviation that you could imagine. Maybe for the first 3 information sets here, the deviation isn't going to modify the strategy at all. It's just going to copy it from the input to the output. But then at this 3rd information set on the left, if the strategy is playing left, it's going to switch that to playing right. And we call this a trigger information set. So the deviation is going to trigger at that information set on that action and change it to right. And then on the next information set, if that strategy had triggered the deviation, then the deviation is also going to always play right in the next information set. Does that all make sense? All right, I'll take that as a yes. Okay, so now how does this actually look to use this deviation? So it looks something like this. So on the left, we have the deviation, which remember is a function. We're going to apply it to the strategy that we had before, and we get an output strategy that now plays left, left, right, right. Okay. All right. Now we're going to need to compress this a little bit, and we can do that actually just by overlaying the deviation on top of the strategy. So now we can see that the original strategy went left, left, but the deviation strategy triggered and went to right, right. And we end up at this LLRR outcome. All right. Now, one other thing that we're going to need is to abstract this out. So this is one particular deviation, but you can imagine many deviations that have this kind of flavor where you follow the strategy for a little while and then you deviate. And that's exactly what are called causal deviations. And we draw them in this abstracted form where we have a zigzag at the top representing an arbitrary string of actions that lead to some trigger information set. And then we have this trigger action in cyan, and that changes the strategy to some deviation action in red. And this triangle just represents an entire strategy that follows the action, and that as well is conditioned on this trigger action. All right. Great. Okay, so we're going to make a lot of use of that. So now I'm going to use those abstract diagrams to describe a large chunk of the space of deviation types in extensive form games. Okay, so here we'll start with the really simple deviation types. At the top here we have the internal deviations. So these are the most general form of transformation you can imagine. They just take an input strategy and map it to an arbitrary output strategy. There's no constraints on how that transformation can occur. And this is the deviation set that's associated with correlated equilibrium, the original correlated equilibrium from Amii. On the other side of the complexity scale is external deviations. This is where the deviation completely ignores the input strategy and just outputs a single fixed deviation strategy. So when you use these deviations, you get coarse correlated equilibrium. Now, in extensive form games, because we have this sequential structure, there's actually deviation types that are in between these classes. Like I showed before, we have the informed causal deviations. Now, they're informed because of this cyan conditioning on a trigger action. In contrast, the blind causal deviations have no trigger action, but they still trigger at a particular information set. And these are the deviation types associated with extensive form correlated or coarse correlated equilibrium. Another class of deviation types that we'll talk about are action deviations. Now these look a little bit like the causal deviations, because they still have a trigger information set, and in the informed case, they also have a trigger action. But after they trigger, after they do one transformation at a single information set, they have to go back to following the rest of the strategy. Since learners, the learner's strategy can be correlated with the strategies of the other players, we say that this deviate and then follow kind of action is recorrelation. The action deviations are allowed to recorrelate, whereas the causal deviations, for example, have to deviate all the way to the end of the game. And these deviations are associated with agent form equilibrium, either correlated or coarse correlated. Okay, so one thing you can notice here is actually that the action deviations are limited in the sense that you can't take an action deviation and deviate all the way to the end of the game, as long as the game has more than one decision point. So you can't represent the external deviations within the set of action deviations, but you can with causal, because causal deviations could trigger right at the beginning of the game. So right here, already we see that there's a weakness in the action deviations. There are easy games you can construct to see that this makes a difference. But what about the other direction? Are there games or situations where you would actually do better if you considered the action deviations compared to the causal or external deviations? There's actually a paper, the original paper that introduced action deviations suggested that maybe they don't, they're actually strictly weaker than causal deviations, but we show that's not true. So that's the first question we're going to address here. And so here's the example. It's an extended battle of the sexes example in our paper. So we have two strategies in this setup, strategy 1 and strategy 2. Strategy 1 will play not u, y and get a value of +2 in the first scenario. And of course, the other player is picking a strategy as well, and they can change. There's a different strategy for player 2 in both of these scenarios. And in the second case, player 1 is going to play not ux and get a value of +1. So then the total value that strategy gets is +3. But if we apply an action deviation, there's actually a really easy way to gain value. All we do is we choose the u action at the beginning of the game, always, and we'll get a value of 3 in the first scenario and a value of 2 in the second. So here you can really see the power of this recorrelation idea. Because the original strategy profile had correlation between the two players, the action deviations are allowed to temporarily break that correlation and then recorrelate afterward to get better value. So we have a beneficial action deviation, but causal, there's actually no causal or external deviation that can do the same trick, because if you trigger at the beginning of the game, you have to continue deviating to the end. So you'll get 0 in one of the two one of the two scenarios, or you could trigger afterward, but you're still in the left information set, but you're still going to force yourself to get 0 under one of the scenarios. So this proves that there's no beneficial causal or external deviation. This is in fact an EFCE, but there is a beneficial action deviation. And knowing that now, we can start to fill in a table of equilibrium relationships. So here I'm showing the cyan cells show where the row concept, equilibrium concept, implies the column concept. So for example, any extensive form equilibrium is also a CCE. And the red cells highlight false implications. So for example, an extensive form equilibrium, as we just showed, may not be an agent form, coarse correlated equilibrium. And the letters that we have here refer to game examples described in our AAAI paper. So we put all of these examples together, even though some of these relationships were known, just for completeness. But the new relationship is the one we just showed, where CCE and extensive form equilibria do not imply agent form equilibria of any kind. All right, does that all make sense? Are there any questions so far? I have 10 minutes, so I will maybe go a little bit faster. All right. Okay, so now I'm going to get into counterfactual regret minimization. How can we use these ideas about deviations to better understand what CFR is doing? And one question that's come up is, could CFR be hindsight rational for one of these deviation types that we've just looked at, the causal deviations or the action deviations? But the answer is no. We have an experiment that shows that if you run CFR in self-play and you check how close its empirical distribution of play is to either an extensive form or an agent form course correlated equilibrium, the gap will actually plateau at something greater than 0. So we know that CFR isn't hindsight rational or no regret for either the causal or action deviations. But is CFR doing something else, maybe, besides being rational, hindsight rational for the external deviations? This was the original, this is the property that makes it useful in two-player zero-sum games. And the answer is yes, actually. We've described a new class of deviations called counterfactual deviations. And CFR is hindsight rational with respect to the blind version. And this is just, it looks like this, where you take a bunch of blind transformations, an arbitrary length sequence of them, to some target information set, and then you leave the rest of the strategy unmodified. So you recorrelate in the same way that action deviations recorrelate. So this is the deviation set that CFR is actually operating on. Using this and kind of adapting it to be symmetric with the informed action and causal deviations, we can get an informed counterfactual deviation where we have a sequence of blind transformations to a target information set. Then we have a single informed transformation, and then again, we recorrelate. And it's actually really simple to change CFR to target these deviations. All you need to do is switch the no external regret learners that CFR uses at every decision point, switch them out for no internal regret learners. This adds a little bit of computational cost, but it doesn't depend on the size of the game, so we're happy with that. Okay, so now we can add those counterfactual deviations into our broader landscape. We can see that they look like a flipped version of the causal deviations, but they have the recorrelation property of action deviations. So that example we saw earlier, actually, counterfactual deviations can get the better value, making it distinct in strength from the causal deviations. And we can recover the external deviations just by deviating all the way to the end of the game and combining all of the external or the counterfactual deviations in just a summed kind of way. All right. So now one other thing I want to mention is that it's actually really easy to modify CFR to target action deviations as well. For those who know what CFR does internally, all you have to do is weight the reach probabilities, weight the counterfactual values by reach probabilities. And this gives you that the algorithm that I mentioned before that is basically PGPI. So now in this picture, you can see those are the deviations that PGPI we're using as these action deviations compared to the blind counterfactual deviations used by CFR. And we can fill in an equilibrium relationship table, the row and column for the counterfactual course correlated and counterfactual correlated equilibria. And you can see that we have some examples where counterfactual equilibria do not imply agent form or extensive form equilibria and vice versa. So they're largely distinct from everything else. And now I want to just give a little hint of what we've done in the follow-up paper to expand this work. You can add a bunch more deviation types. So here I've added what we're calling partial sequence deviation types. They're highlighted in bold. There are 4 different versions. There's blind partial sequence, causal partial sequence, counterfactual partial sequence, and twice informed partial sequence. And they're all subsets of a larger but natural class of deviations in extensive form games called behavioral deviations, where you have independent transformations at every decision point. Ideally, you would actually just target the behavioral deviations and kind of be done, since it's a very general class of deviations. The problem is that the algorithms that we have, it appears to not admit an efficient algorithm in terms of the length of the game. So the amount of computation and storage that you need to target the behavioral deviations grows exponentially with the depth of the game. So in really long games, this isn't going to be feasible. But what's special about the partial sequence deviations is that they're actually efficient, even though they're stronger than all of the other deviation classes that we've talked about so far, the causal, the action, and the counterfactual deviations. So this makes them really nice for implementing, because you don't have that computational cost, but you still get the extra power. So we have the amount of computation grows polynomially for the partial sequence deviations. And future work is to actually improve even that. So I also want to point out that EFR instance that I showed at the beginning of the talk in the experiments was using the twice informed partial sequence deviation. So stronger than both, than all 3, causal, action, and counterfactual, and the informed versions as well. All right, so with that, I'm going to go into to conclude the talk. So Hindsight Rationality is a theoretical base for playing multiplayer general sum games. Algorithms designed for stronger deviation types tend to perform better, as I showed at the beginning of the talk. The deviation landscape in extensive form games is both rich, but also counterintuitive at times, because a lot of the things we showed in this talk seem now a bit basic, but we spent a long time in discussions trying to clear up previous misconceptions and misunderstandings, and we're hoping that this paper can act as a base for more interesting things going forward. We showed that CFR minimizes regret for counterfactual deviations, but not for causal or action deviations. This was also claimed in a couple papers, and I think it might still actually be in one paper. So yeah, definitely we're happy to clear that up. And I also mentioned that CFR can be modified to target alternative deviation sets without too much trouble. And we go into that in a lot more detail in the follow-up work. Some remaining open questions. Stronger deviation types require more computation. So what should we do about that? One thing I'm excited to try working on is that the problem that you get with stronger deviation types is really the same problem that comes up in other scenarios where you have many. It's called the many experts problem. So like this comes up in tracking or in trying to compete with large like tree structure experts. So maybe we can adapt those same kind of approaches to get efficient, and we have efficient algorithms in those scenarios, like the fixed share forecaster or context tree weighting. And so maybe we can adapt those to give us a little bit of the best of both worlds, where we can target the behavioral deviations, but we don't, or at least we have some sliding scale between the complexity of the deviation and our performance guarantee with respect to that deviation. Another challenge is taking these ideas and scaling them up, because all the work that we've done so far has been tabular in really small games. So the algorithm that we have, EFR, is you can apply sampling and function approximation techniques that were previously developed for CFR, you can just apply them right out of the box. But how well does this do? How do the performance improvements shake out when you actually move to that setting? That we don't know yet. And another thing, as I mentioned before, it would be great to move beyond both uniform hindsight rationality, so weighting all the rounds evenly, and also move out of extensive form games to a more general continual learning kind of setting. And so these are both things that we're thinking about going forward. All right, and that's everything. Thanks so much for listening. I'll take questions or comments now.
I've got a question. It's Rob Holte here. So if you were playing multiplayer poker, like, I don't know, 5 players or something like that, and every one of them was doing exactly the same thing in terms of, using the same deviation and the same algorithm and stuff, what would happen? Would they just break even?
Well, I mean, we know that the strategies that they'll produce over time will form a mediated equilibrium with respect to that deviation set. But the dynamics could cause the players to cycle. So this is like, there are famous examples like Shapley's game, right, where you have learning algorithms that their behavior will just continually cycle. They'll never converge on anything. And so that's what you'll get here. But the idea is that the players end up, they converge to like a correlation. So they're going to move in sync according to these, according to the equilibrium, like to follow the equilibrium behavior. So that's really all we can say. And the idea would be that if you, I mean, they are going to guarantee a minimum performance guarantee with respect to the players that the other strategies played, looking back on average over time, with respect to whatever deviations you set out. I guess maybe one other quick thing about that is just, we don't intend for these learning algorithms to ever stop, right, or converge. The idea is that they're continually adapting. That was going into the continual learning extension. Hi, Amii.
Hi, I was going to ask you more about the continual learning extension. I mean, maybe just like high level, what kinds of ideas do you have moving in that direction?
Yeah, I mean, it's tricky because all of the work that we've done so far has these pretty strong assumptions about the structure of the information that the players get, like that they remember all of the decisions that they've made up till the end of the game, and then the game actually ends and you only get payoffs at the end of the game. Whereas if they get payoffs as they're going, now you have to think about, like, what information do those payoffs reveal about the environment. So it does get complicated. Yeah, it's something that we've just started talking about. And I think the first thing to do is really to nail down the theoretical base. I know there was a talk recently that I think Van Roy gave, talking about like a general, not quite an MDP, but a learning scenario where you just continually get observations and rewards and you take actions, but that's all you can say. And so maybe adapting something like that would be useful. It's unclear exactly what we'll be able to say in such a generic setting. I guess the other extension is that there could be state that the agent is constructing in their own mind, and we could say things about the kind of a game that's being constructed by the agent itself. So maybe that will be one route to get results.
Sorry, I'll ask one more.
Sure.
You said there was some computational disadvantage to using the most general. Actually, I have two questions. I'll ask the more interesting one first. So you have this gap between the behavioral guys and the twice-informed PS. And the behavioral guys, you thought your present understanding is that it's exponential computation, and the twice-informed PS is not, it's polynomial. So is there anything in between those, or do you think that twice-informed PS is probably the limit of the polynomial options?
Right. So there are definitely other polynomial options here. What makes the partial sequence deviations nice is just that they subsume all the other ones that people.
No, that's why I'm asking if there's something above them.
Right. Well, anything above them will have just more computational cost. I don't think there's any extra power that you can get for free with this. The best you can get for free is kind of the counterfactual deviations kind of represent what you can get for free, because you in fact only need as many counterfactual regrets as there are information set actions rather, and that's the same number that you need for action deviations as well. You need a few more for the informed counterfactual deviations, but it's all localized to a particular information set. So we can scale the game as much as we want, and it doesn't really matter as long as the action set is smaller. So those you kind of get for free. Anything else, whenever you introduce like conditioning, like you introduce informed deviations higher up in the tree, then the information set lower down, right, that has to deal with the possibility of a deviator changing strategy either away from or to this information set, you need to keep track of extra information for that and do extra computation.
But you said it was polynomial.
Yep. Yeah. So the growth, the amount, whenever you introduce an extra informed deviation, you add computation according to the length, like linear in the length of the game, essentially, because you have to consider the information set at the very end of the game. That's where you're going to have the most the maximum number of regrets to keep track of. The only case where this doesn't happen is informed counterfactual deviations, where you immediately recorrelate after the information about the strategy is given to you, after you do that one deviation. So it is really like a conditioning thing. Like the twice informed partial sequence is expensive, particularly because we continue deviating after we get some information about the strategy that we condition on. And actually, in fact, the informed causal deviations are already more expensive than both the action and counterfactual deviations.
Okay.
We've got a question in the chat. I don't know if we covered this already, but Derek asks, does the deviations represent any form of uncertainty measure?
I don't think they represent uncertainty. To me, they represent something about how adaptable you need your learner to be. So for example, if you just chose the external deviations as the deviation set, you're implicitly saying, I don't really need this learner to adapt too much. I just want it to be as good as a single fixed strategy, right? If it finds that fixed strategy, that's good enough. The stronger deviation types, like you can go all the way to external or internal rather. It's saying something like, every time that the strategy zigged, it should have zagged, right? This is a stronger adaptive kind of property than just saying it should play one fixed strategy. It's, it's almost, it feels a little bit to me like a coach, saying ahead of time, like, you need to watch out for this because this is where the value in the game is going to be, right?
Can I ask another question?
For sure.
So this picture is a little nutty, like it's kind of crazy. Like, what should our takeaway be? Like, can we like imagine a smaller picture, like with a little less information that I can like maybe remember from this whole story?
Well, I mean, one thing you could do is, oops, sorry. You could just maybe ignore, if you wanted to, the kind of the intermediate ones, like the causal and counterfactual partial sequence ones. The blind ones are partial sequence are kind of interesting just because they're cheaper, but they still subsume all the blind versions of the deviations. So yeah, twice informed is kind of the major umbrella deviation type that if you ask me what you would want to implement, in an arbitrary game, I would probably say either twice informed partial sequence deviations or informed counterfactual deviations. Or if you're, or sorry, actually, I would probably say twice informed, then maybe the blind partial sequence deviations. If those are too expensive, then informed counterfactual. If you have too many actions, then blind counterfactual. I mean, this also goes to like the richness of extensive form games, but sorry, go ahead.
No, absolutely. You didn't mention causal because like partial sequence is maybe as expensive and not having all the benefits.
Right, yeah, so in fact, there, at least within the CFR kind of framework, there's really no way to directly target, to directly target the informed causal deviations. It is exactly as expensive as running the causal partial sequence deviations. And it's not clear that there could be any gain there. So the one previous, it's also in the CFR family, but another author, Celli, has an algorithm, a CFR-like algorithm for informed causal deviations, but it's actually targeting the causal partial sequence deviations. We just didn't have the terminology before that.
Thanks, Dustin. I gotta run, it turns out.
Sure.
Thank you all. See you later.
So we're just past 1 o'clock. So if no one has any other questions, I think this is a good place to end it here. Thanks very much, Dustin, for presenting. If anybody wants to meet with Dustin to discuss this further, you can either send me an email, I can help coordinate, or you can email Dustin directly. So yeah, thank you again, everyone. Have a great weekend. And we will see you next week or not next week because it's Good Friday, but we'll see you in 2 weeks for the next AI seminar.
And thanks again for having me.
No problem. Bye.